Hello student to the Foundation of Classical Electrodynamics course. So, we are still in module 1 learning the mathematical preliminaries. So, today we will going to understand the Helmholtz theorem. Okay. So, we have today class number 18. I am going to learn about the Helmholtz theorem, but before that we need to understand a very important identity, and that we are going to prove today, and the identity is this. So, if I want to find out the Laplacian of a scalar field defined like this is a distance function, but the scalar value I am taking, then that value is equivalent to minus of 4 pi and then delta function in 3 dimension r minus r prime. This is a very important identity that regarding the delta function. We already understand delta function in last couple of classes. So, we are going to exploit its identity, those identities to understand this expression, how these things are there. So, here if I now, so this is my coordinate system, say, and in coordinate system if I plot my r here and r prime here. So, this is a point r and this is r prime. So, this distance is simply vector r minus r prime, vector r prime. So, this is the system we are having. Now, you can see that for r not equal to r, first we will do for r not equal to r prime. If I calculate this quantity, this quantity simply comes out to be 0 under this condition. How? Let us check. So, let mod of r minus r prime to be curly r. Okay. So, then eventually I am calculating this quantity mod of r minus r prime. So, this is equivalent to Laplacian of 1 by curly r, that I am calculating. Well, now with the brackets here. Now, this quantity, this Laplacian, I am operating over a function 1 divided by r. So, this Laplacian operator should be in spherical polar coordinate system, because my function, whatever the function I am having, which is 1 by curly r, is in polar coordinate, spherical polar coordinate. So, and also the theta phi is not there. So, the derivative with respect to theta phi will not going to play any role here. So, if I just only expand this del square operator in r theta phi coordinate, the r part of that, it simply gives us 1 divided by r square del r and then r square del r, and that we are going to we will going to operate over 1 by r. That is the operation we will have. Now, here one thing you should note that the curly r is not equal to 0, because that is the condition we had here, because curly r is r minus r prime and r is not equal to r prime. So, if you make a mod sign of r minus r prime vector, then that value should be a non-vanishing quantity. So, then the rest thing is mechanical. So, we have 1 divided by r square, and we take the coordinate system in such a way that r minus r prime is, that means I am putting my coordinate system over this r prime. So, that r minus r prime became the the radius of this sphere over which we are calculating. So, then it is del r, and we are having r square here multiplied by minus of 1 by r square, because I am having a partial derivative 1 by r partial derivative with respect to r of 1 by r. So, it should be minus of 1 by r square. So, then we simply have minus 1 by r square del r, and this will cancel, and we have minus of 1 here, which is a constant. So, this simply gives us 0. Okay. This simply gives us 0. So, now we will going to check the other thing, that is what happened when r is equal to r prime, r is equal to r prime, that is the point. So, I am just having this r over this r prime. So that this whatever the value we are having is 0. So, r at r prime, what we get, that at r equal to r prime, what we get, that we are going to do here next. Okay. So, for this case we can consider. So, let S is a spherical surface of radius say of radius r. Okay, this is another radius, I am using the same. So, centered on r equal to r prime. So, I have a spherical surface whose center is at r equal to r prime with radius r. Now, if I want to calculate the ds element, the surface element, it should be simply r square sin theta and then d theta and then d phi and then r unit vector. So, this is the surface element we know well. Now, if I calculate this quantity, the divergence of 1 by r, it simply gives me minus of r unit vector r square. Okay. Now, why I am doing this? Because I want to calculate this quantity. This is a Laplacian and I want to calculate this quantity. This quantity is equivalent to the divergence and of the gradient of 1 by r. The divergence, the gradient of 1 by r, that we know, in the previous class we already mentioned. Now, if I calculate this integral, a volume integral in this way, because I am taking a surface element here, so I can calculate the volume element of this quantity, which is 1 divided by r and dV, then that is, according to the way we derive it here, it should be simply the divergence of the gradient of 1 by r, curly r. And then dV. Now, exploiting this is our volume, exploiting the this divergence theorem, I can write it as the closed surface integral of this quantity I put the vector sign here, I put the vector sign here, of this quantity over this ds that we calculated earlier. So, if I make a divergence, I know what is the value. This value is minus of, still I have a closed integral r unit vector r square, and then the ds is simply r square sin theta d theta d phi and this r unit vector, this is r. Okay. Now, this r square will cancel out, that is the interesting part, this r square will cancel out, and eventually I get minus of integration 0 to 2 pi for d phi, and then integration 0 to pi for sin theta d theta, and that quantity is simply minus of 4 pi, it is not equal to 0, it is minus of 4 pi. Okay. So, now I have two conditions, one is this. So, one condition I have is this one, del square 1 by r is equal to 0 when r minus r prime is equal to 0, and another condition is this, that integration of del square 1 by r dV is equal to minus of 4 pi. Okay. So, where V is a over this volume integral, here you should note that V is the arbitrary volume surrounding the point r equal to r prime. So, B is the point V is the arbitrary volume that is surrounding the point r equal to r prime. So, now combining this 1 and 2, we can write a very nice equation. So, combining equation 1 and equation 2, we can write that del square 1 by r is equal to minus of 4 pi, and I can associate this delta function, delta cube should be called here. This where r prime. Why I put this delta function? Now, from equation 2 I can see that. So, if I use equation 2, then we have 1 by r dV, and that quantity simply can be written as V minus 4 pi, because this quantity I write it here, and then delta function over this r dV, and this simply give us minus of 4 pi, and this entire integration should be 1. So, I will get minus 4 pi, which is equation 2. So, that means I am having a very important expression here, and that is delta square 1 by mod of r minus r prime is equivalent to minus of 4 pi delta cube r minus r prime. Okay. And also from that we can write another thing, that from here it is consistent that del, if I make a divergence of this quantity r minus r prime divided by mod of r minus r prime cube, then that quantity should be 4 pi then delta cube r minus r prime. So, this is consistent because you just need to expand this thing. So, take it as a homework. So, please try to find this correlation. What you need to do here, I am giving you the hints. So, delta square 1 by r is simply del dot this 1 by r. So, you can expand these things in this way, and then the rest of the thing is followed. You just need to calculate this del 1 by r where r is r minus r prime, and these things will follow, simply follow. Okay. Now we are in a position to discuss about this Helmholtzs theorem. So, Helmholtzs theorem. So, before going to the detailing of the Helmholtzs theorem, let us write this. So, if say let us consider if R is a vector field, if R is a vector field which is a function of position. Okay. Now, in general, this vector field f r can be represented as this way. This can be represented as a gradient of a scalar function plus curl of a vector field. That means a vector field can be decomposed into two parts. One is this one and another is this one. So, I can decompose this vector field into two parts, and where f is a scalar field and v is a vector field. Now, the question is the choice of, so if f r is given, if this is a given vector field, the question is, can I construct f and v? The answer is yes, we can construct f and v in such a way that the scalar field, the gradient of the scalar field and the curl of the vector field, the combination of these two can give rise to whatever the vector field is given to me. So, I can construct this vector field by choosing properly f and v, but the question is f and v is unique? Can I choose uniquely? So, that let us take. So, the answer is it is not necessarily unique. So, I should write it here. So, here the decomposition into a gradient and a curl is not necessarily unique. An example can be given for like if suppose a constant vector, simply constant vector, lambda is a constant. So, lambda here is constant. So, this is it is given. So, I can construct my L in this way. So, I can construct f like minus of z lambda and v as 0. This is my choice 1. With this, can I get my f? Let us do. So, if I want to find out this quantity, what we get? Divergence of f of this, it should be simply minus of lambda k. If I want to find out the curl of this quantity, what we get? Curl of V, it will simply give me 0. So that means this with a negative sign plus this simply give me lambda, maybe I can put it in different color, give me lambda k, which is my function, given function f. Okay, that is the given function. So I can construct f and v suitably such that this decomposition works. Now this is my choice 1. Now I can make another choice. I can make another choice, my choice 2. So let us make another choice. The second choice is simply I put f equal to 0 and v equal to x lambda I. This is my choice. F equal to 0, v. Should they produce the same vector field? So f is 0 simply gives me the divergence, the gradient of f is simply 0. What about this? What is the curl of v now? The curl of v I need to calculate. It is I j and then k, I j k del x del y del z, and the component, the x component, okay, this is not I, this should be z. This should be j. So it should be 0 and then lambda x and 0. If you execute that, you will find it should be simply lambda k. It should be simply lambda k. Okay, so that means if I add these two quantity for this given an f, given f and v, I will get back lambda k like previous way, which is the given function f. So for the given function f, I can construct two different f and v, and both cases this decomposition, whatever the decomposition I am saying, okay, I should have put a negative sign, and this negative sign is a convention. I must say here, this negative sign here, the way we put to define a vector field in terms of a gradient of a scalar function and curl of a vector function, and this negative sign is a convention to put. There is no special reason to put this negative sign, but later we will find that this leads to some sort of potential, and that will go to, I mean, normally there is a for potential we put a negative sign, and that this carry through. So we can see that two different values can give the same. Now let us go to the Helmholtzs theorem, the statement rather. So again I am writing here. So suppose we do not know a vector function Suppose we do not know a vector function fr, the vector function, this is not known, the explicit form of this vector function is not known, but we do know its divergence and curl. This is important. The divergence and curl of this vector function is known. So, let me write it here clearly. So, what it is saying, that it is saying that this function as a whole is unknown. But these things is known, the divergence of this quantity, whatever the unknown function I have, the divergence value, say equation 1a, and the curl of that quantity, that vector field, is separately known, say C 1b. These two is known. Note that once we know this equation, it readily gives us another information, and that information is this, the additional information we are having here. The additional information is, since equation 1b is known, if I make a divergence of that curl of f, because C is known, that means it is dot C. So, this has to be 0, because divergence of curl of anything is always 0. So, I have an additional information here, that this is the additional information, that divergence of C is 0. So, I have 3 information in my hand. One is the divergence of f is d, this is known, the curl of f is C, this is known, and from this equation 1b I have an additional information that is here. So, let me write it 1c. Now, next thing, I am not going to prove that, as I mentioned in my, so we will like to know, we will like to know, we will like to know if equation 1 means 1 ABC, all these 3 equations provide enough information provide enough information provide enough information to determine Fr uniquely. So, the point is this is known, the curl and the divergence and curl of this function is known. Now, the question is it enough to to construct FR uniquely, and the Helmholtz theorem is suggesting that FR can be determined, FR can be uniquely determined uniquely determined if this d, which is a function of r, the divergence function, and c, which is a function of r, vanishes fast enough as r tends to infinity. So, this is the condition we have. So, this condition, as I mentioned, it is difficult to prove because this is a lengthy proof. I will show you first the thing. So, then I am going to explain. So, the recipe, so how you find this? The recipe is recipe to determine FR. So, if I can divide it in this form, as I mentioned, this plus I can decompose in this way. Any given function, any given vector function I can define in this way. Now, I can construct my f, that is the interesting part. I can construct my f exploiting the value of d, which is known, and the result should be this. Fr should be 1 by 4 pi, then integration, this d is known, which is a function of r, divided by r minus r prime dv. This is the way I can define my Fr, because this is known. So, this quantity is known. So, that means I can execute this integration and I will figure out what is my f. Similar way, my v, which is the vector field, which is here, can be constructed by knowing the curl value, and this is simply C r and r minus r prime. Here should have a dv prime, there should be prime, because this integration is over r prime, and here also this is known. This is known. So, that means I can construct my f, try to understand this. So, I can construct my function f, this I can construct, this is unknown, but d and c are known. Once d and c are known, I can construct, exploiting this known c and d, I can construct f and v, and this f and v I can put it here in this equation to figure out my f. So, this is a very very important theorem, because later we will going to use this directly when we deal with electric field and magnetic field. So, today I do not have much time to discuss. In the next class again we will going to discuss this Helmholtz theorem quickly, and then we will going to finish our mathematical preliminary portion, that is the module 1, and then we will going to jump module 2 where we start the electrostatic in vacuum. So, with that note I would like to conclude here. See you in the next class. As I mentioned, in the next class again we will come back this Helmholtz theorem part and discuss few things, so that your understanding is very much clear, and then we jump to the electrostatic part. Thank you. See you in the next class.